Hi everyone. I'm Alex Kreese. Welcome to today's webinar on designing for 3D printing, making the most out of additive manufacturing. I'm an application engineer here at Markforged, and I'm here with Daniel Leong, another one of our applications engineers, and Cynthia Gumbert, our VP of Marketing. So just a brief agenda for today. What I'll primarily be discussing is sort of how to effectively design for 3D printing, what kinds of things you have to keep in mind, and a little bit of tips and tricks that I've picked up over the course of a few years working in the industry, and our suggestions both with regard to 3D printing in general and 3D printing specifically for our printer. So I'll be going over an introduction to Markforged for those of you who are unfamiliar with us, basic design for manufacturing, the basic design for manufacturing process, 3D printing considerations, overhangs and supports. Then I'll talk a little bit about part orientation, preventing warping, and finally tolerancing and unit tests, which will allow you to save a lot of money and time 3D printing parts so that you can get the parts that you want right off the print bed. So now I'm going to pass it over to Cynthia Gumbert, who will introduce the company.
Hello, thank you, Alex. Welcome to everybody for joining us today. This was a very popular topic, so I wanted to come in and just give a brief introduction to Markforged. I know many of you are kind of new to the company. This might be the first Markforged event you've attended. Some of you are existing customers of ours and using some of our printers, as well as working with some of our network of resellers. This is part of a monthly webinar series that we do, so stay tuned for more coming in the future. Alex and Daniel, who are here today, provide best practices, tips and tricks, as well as talk about new product and materials introductions that we do periodically. So for for this event, just as an introduction to who Markforged is, we work with manufacturers and engineers to really support product innovation and product development by enabling same-day strong parts. So we're all about strong printing, and the strength in our prints comes from fiber reinforcement. You'll hear a lot of that today from Alex talking about designing for fiber reinforcement and designing for strength. We also just recently introduced metal 3D printing, so everything that we do as a company is support strong parts through 3D printing and additive manufacturing. Markforged was founded in 2013 by Greg Mark, who is our CEO and founder. We're headquartered here in Cambridge, Massachusetts. Spring is kind of beginning to come here to Massachusetts. We've got hundreds of resellers. We're sold through a distribution network that's worldwide, and there's a local demo of a printer likely near you in over 50 countries of the world, around the world. We got thousands of customers. We're funded by venture capital from Matrix Partners, Northbridge, and Trinity Ventures, and growing very, very quickly around the world. We've had some recognition. We've been on the Discovery Channel, and there's a lot of write-ups on Markforged printers within excuse me, a lot of the 3D print industry publications. There's a lot of forums out there with our customers talking about using our printers for various innovations and things that they're doing. And we've been up for awards at South by Southwest, as well as TechCrunch recognition, and now 3D print industry has nominated Markforged for Industrial Printer of the Year. So we can send that out if you guys want to vote for us after this, but just a little bit of recognition. Our customers are global. We've got folks around the world using our printers today, and we have some of the biggest names across multiple industries using Markforged printers for strong parts, for tooling, for fixtures, various manufacturing applications. And before I pass it back to Alex, here's a little bit of an overview of where our parts are used. They're in everywhere where strong printing is required, and especially kind of that upper left corner, we're in a lot of tooling and fixture and production environments where strength, where weight is important, but also in end use. Drones are a popular use of our printer, as well as some prosthetic and orthotic applications. So quick overview. Now back to Alex for the rest of the presentation.
Great, thank you. And just to confirm, we have some people saying that the audio is cutting out. Can everyone hear? All right. Okay, great. So thank you, Cynthia. And so now we'll move on to sort of an overview of design for manufacturing. So in general, in sort of a design workflow, whether you're an engineer, a designer, the usual process, you come up with that idea, you model it in your CAD program, you draw it up, then you go to your manufacturing and design process, and then you have your final product. And this is sort of an ideal workflow that doesn't really have a lot of sort of the hidden factors in designing for the manufacturing process and iterating upon your ideas and stuff like that. So in reality, there's this sort of feedback loop of you come up with your idea, you start to sketch it out, you start to draw it, you start to model it, and then there's this cycle of iteration and improvement in which you're designing to improve your manufacturing process, to improve the functionality of your product. And what a lot of engineers and designers do is start with a rough sort of model before deciding upon a manufacturing process. And through iteration and improvement, V2 is always going to be a little bit better designed for a specific manufacturing process than V1. And every sort of step of the way, there's always room to improve the design of a model, because there's always ways to make the manufacturing of that part easier. Whether it's a CNC machine, a 3D printer, a laser cutter, design for manufacturing ensures essentially that you get reliable parts that can be produced easily. So why design for manufacturing is important is sort of on the evaluation side, you can save a lot of money through implementing effective design for manufacturing. So a part that you machine on a mill, your first revision of it may take 5 hours to machine, but your second, because you were able to eliminate, a tool holding change, could take 3 hours, and that saves manufacturing time, which saves cost, which saves, which sort of increases efficiency and sort of decreases time wasted. So in every sort of manufacturing process, there's always ways to evaluate how to make your design more effective. One example that I always like to talk about is sort of hand drills. The shell of the hand drill is this complex injection molded part, but the way that it's designed means that an entire hand drill, if you take like a DeWalt drill or something like that, can actually be assembled in under 2 minutes. So the part is very well designed for assembly, because they want to produce thousands of these a day. So everywhere in the design process, you can really increase your productivity and design efficiency by critically considering your manufacturing process and what its benefits and drawbacks are. So for example, we start with sort of a block rough CAD model of an enclosure on the left here. This enclosure, depending upon what manufacturing process you decide, can be optimized to suit the the efficiencies of that manufacturing system. So for example, on the bottom, if it were to be laser cut, you'd have to split it up into a bunch of flat pieces that you would then glue together or bolt together and use maybe standoffs or spacers to get the threads where you need them to be. Um, and this would be very different from 3D printing that part, which would probably take longer than laser cutting to manufacture, but give you a higher quality, a like more final looking model. You'd need to have heat set inserts for the threads that you see in the model, and you would design it to be a little bit more sort of natural and curved aesthetic. Whereas if it were machined, you'd probably have to do some amount of design work to optimize for what type of bits you're using, what stock you're cutting from, how you plan to hold that stock, and how you plan to deal with things like if you need a sharp corner in when you're machining something, how you go about doing that because the bit is often round. So every process sort of requires this step of making sure that you can actually manufacture it given the manufacturing process you've selected. A lot of the way that 3D printing is portrayed is sort of as this tool that can create anything. And what our sort of thoughts on that are is that 3D printing is just like any other manufacturing process. It has some really amazing benefits, especially with our printers. You get parts that are nearly as strong as metal. You get parts that are very precise, very high quality surface finish. But designing with the process in mind is still a really, really important step because it will guarantee quality and reliability in the parts that you're printing. So if you start your design with the idea that you're going to be 3D printing it or you're going to be making it out of sheet metal, that will be able to improve your design workflow. And in order to do that effectively, having a good understanding of what the limitations and what the pros and cons are of the 3D printing process as a whole. So we're going to go through some of those pretty quickly just so that you have an understanding of where 3D printing can be really valuable and where other manufacturing processes may be better. So in terms of our type of 3D printing, FFF 3D printing, so fused filament fabrication, the process is layer by layer. So you're laying down sort of beads of material on a build plate, building that up layer by layer. So this, where a lot of 3D printers sort of, where the design for manufacturing for 3D printing on any sort of FFF 3D printer comes into play is in the geometry limitations of this process. So that includes the support and overhang angles. That's based on material. That's based on sort of how supports are generated. The z-axis strength of the material itself. So how can you orient your part to be stronger, to be strong where you need it to be strong? 3D printing in general is a relatively slow process compared to things like laser cutting or things like that, but ends up being much faster when it comes to things like using a service provider to order CNC machine parts from. So a lot of these specifications are dependent upon the printer, but in general, the additive process means that the layer by layer process has geometry limitations. Where our printers are really unique is in their ability to lay continuous strands of fiber inside of the parts. So here you see one of our two sample parts actually. This one is our sort of plain nylon sample part. So on the inside you have infill. That part is printed without fiber reinforcement, and that makes it end up being very weak and very flexible. This part over here is printed with our secondary plastic material, which we call onyx. And on the inside is where our sort of the strength of our parts comes into play. So you'll see here, this is how it looks in our software. This is how it looks in the actual part if you were to open it up. There are continuous strands of carbon fiber running up and down this part, and that's what makes it really strong. And so you can optimize for that you can control how much fiber you're putting into your parts, and so that's what makes our printer stand out. It's the part strength ends up being comparable to metal because we're able to lay down continuous strands of fiber inside of our parts. Um, some of the considerations are because the fiber is being put down inside of parts, there are some small feature reinforcement has its limits, just like any sort of small feature capability of any sorts of 3D printers. And as I said before, with 3D printing in general, while it may seem like a fairly slow process, it ends up being a lot shorter than CNC machining parts often. And so there is additional manufacturing time if you reinforce your parts more heavily, but in general, you're getting parts that are stronger and more affordable than parts that you could machine via a service provider, because machining a part could take 2 weeks and cost a few $100s, and you could print that same part, have it be just as strong, print it overnight, and ready to mount on your product the next morning. So one of the big geometry considerations of 3D printing in general is the sort of minimum wall thickness and detail that printers can hit. So on our printers, we can hit about 1.6 millimeter wall thickness is the thinnest part we recommend, thinnest feature we recommend including in designs. So basically why that is each strand of fiber is 0.4 millimeters thick. So when you get down to really, really small wall thicknesses, you want to have at least 4 walls. So that means at least 4 strands of fiber. For detail features like engravings, embossings on your parts, the filament can sort of extrude outwards and then come back into the part. And so we generally suggest 0.8 millimeter thickness for details that are on the faces of different parts. These screenshots are all from our Eiger software. It's how we slice our parts for printing. So you have control over infill settings, the slicing settings, etc. And then you also can control on a layer by layer basis how fiber is reinforcing your part, and we have settings that we optimize for that. So in general, overhangs are another big sort of design consideration in 3D printing. Our onyx material is capable of supporting itself up to sort of 60 degrees from the vertical. So our supports usually kick in at around 45 degrees, but usually we're able to do a little bit more than that. The overhangs end up being really important because if you want to cut down on material usage and cut down on print time, then you can use the overhang angle to your advantage when you're designing to remove support materials, and I'll talk a little bit about that later. In terms of the sort of minimum detail feature size, vertical posts and minimum hole diameters are another key consideration. So we recommend about a 2 millimeter diameter minimum post size recommended. This is sort of for a similar reason as I explained to you before with the minimum wall thickness, where you need a certain amount of rings of filament being laid down to create the part. And for hole diameters, we suggest no smaller than 1 millimeter because the hole will essentially end up closing if it gets too much smaller than that. A lot of these are very common to many sort of FFF 3D printing processes because we're working with thermoplastics, and thermoplastics sort of have their own set of requirements when it comes to how they can behave when extruded. Now we get on to the fiber reinforcement aspect of our printers. So as we sort of described earlier, how our printing process works is we have 2 nozzles. One of them extrudes that plastic, which I've talked about up until now. The other one lays down continuous strands of fiber inside of your part. So the fiber is always going to be reinforcing on the inside. because it's being placed inside of the walls of your part and you have some amount of control over that on a layer by layer basis, it's always going to be trying to sort of find a loop in your part. So our general reinforced wall thickness minimum is 3.8 millimeters. There are exceptions to that. For example, on the right here, we're able to fit one strand of fiber inside of this sort of loop extrusion because it can loop back in with the rest of the part. So if the feature is able to form a loop, then you can create a 2.9 millimeter wall. If not, then stick with 3.8 millimeters, and that will guarantee that fiber is able to fit into your part. The fiber additional sort of considerations are that because we're laying down fiber sort of in this inside of the parts, the fiber has a minimum required length. It has to be 45 millimeters or longer to be able to fit inside of your part. And so that means that when it comes to very, very small features, fiber may not be able to fit. And that's a big consideration in our printers. So a lot of our customers will use our printers for things like tooling and fixtures, prosthetics, and equipment. And they're often printing these larger parts. And so the geometries that you can reinforce can only go so small because the fiber is continuous. So we need to be able to specify a length of strand that can fit into the part for it to work well. In every layer of fiber, so when you lay down a layer of fiber, the software creates sort of roofs and floors over that layer. You can stack multiple layers of fiber on top of each other, but if you want a single sheet of fiber and the minimum thickness of part reinforced with fiber, so if you just had one layer of fiber, it would have to be, it would require a certain number of floors and a certain number of ceilings on the top and bottom of that layer. So it's essentially a 9-layer minimum. With fiberglass, you get that creates 0.9 millimeter minimum height. With carbon fiber, that's 1.125 because it's a little bit thicker. So carbon fiber prints with a 0.125 millimeter layer height, whereas fiberglass, Kevlar, and HSHT print in a 0.1 millimeter layer height. So, so this red band here is representative of one layer of fiber. If, say, you had 10 layers in your part in general, and it was 1 millimeter thick, then you could fit 2 sections of fiber in there. And so as you increase, you can just fit a lot more fiber in, and so the roofs and floors end up taking a fraction of a percentage of the total number of layers. But in these small, in very small, very tightly packed parts, these are sort of the minimum details that you can hit with fiber. Okay, so now we're going to go on to talking about overhangs and supports. So in general, our support material, as you can see here, you just sort of peel it out. It's this accordion-like structure that you can remove easily from the undersides of parts. It allows for printing direct overhangs, but designing to minimize supports is something that we often practice here because it allows you to cut down on print time, cut down on material usage, and that ends up saving a lot of time and saving a lot of money in some cases. So parts can be designed to minimize support material, considering those overhang angles I discussed earlier. So what I often suggest to people is to angle overhangs where possible to create parts that don't need that don't need support material. So this pulley over here, you could take this pulley and instead of printing with flat faces on the top and bottom, you can slightly angle those with that 60-degree overhang. It's actually 45 in this image, but that allows you to print that pulley with no supports at all. And in a small case like this, the print time is maybe saving 20 minutes, half an hour. On much larger parts where you're doing much more complicated things like this one over here, this part can be printed with no support material because of the way it's designed. So our printer can handle these sorts of overhangs and vertical holes, no problem. And so if this was a flat overhang, if a lot of the features inside had direct flat overhangs, then it wouldn't, then the print would end up taking a lot longer time. And again, you can save money and material um, by just designing for overhangs. Other techniques for minimizing support that we suggest is to sort of think critically about your part orientation. So there may be some orientations of your part that will non-intuitively take a lot less time. So over here we have a sort of leg guard for a skier. Printed like this, it takes 16 days. Printing upside down, it takes 2 days. So this is a very large print, but it's just an example of the magnitude of material and time savings that you can save if you consider the orientation of your part and what is affecting the support material generation. Another option that I often suggest is splitting the model into multiple parts. Not only does this allow you to optimize the strength of your part in specific directions, but it also enables you to use the 3D printing process at what it's good for, which is making these like really nice smooth surfaces, but that's not always true for the undersides of parts. So for example, if you tried to print a perfect sphere, then supports would generate underneath that, underneath sort of the bottom of the sphere, and you would be able to, you can split that part up and print it in 2 halves that you could then adhere together afterwards to cut down on the print time and also to get a much smoother finish on the surface of the ball. If you're more interested in sort of joinery options, then we have a couple blog posts that we've written in the past that discuss different ways that you can use 3D printing to create, use different joinery techniques for 3D printing. And those are accessible on our blog. So the next big thing is part orientation. So essentially, part orientation is critical in 3D printing because that's really where the strength plays a big factor. If your part is going to be loaded in a specific direction, we often advise laying it out on sort of the XY plane. So if we go back here, this is sort of how we're considering. This is how we consider our sort of reference geometry, where the XY plane is parallel to the build plate. The XZ plane and YZ plane are perpendicular to that, and the Z-axis is normal to the build plate. So when you're loading sort of along strands of fiber, where you're either trying to bend them or trying to pull them, that is where parts end up being strongest. This is both with normal plastic filament and also with fiber reinforcement, because that's where the fiber is really powerful. That's where the continuous strands are being loaded in the direction that they are meant to be loaded in. So the parts are strongest when the strength is parallel to the build plane. If you know the loading conditions of your part, then you can design with that in mind. The Z-axis, on the other hand, in many 3D printers is what ends up being the weakest direction, because the layer adhesion is often going to be weaker than the sort of tensile strength of the material itself. So it can often shear or pull apart. With our and this is a drawback in many 3D printing processes, because you're always going to be building things up layer by layer. You can the Z-axis is going to be weaker than X and Y. Let's see. So with that in mind, designing with a build orientation in mind is a very powerful sort of tool for designing parts for 3D printing effectively, because it allows you to reduce supports, reduce material, and reduce print time while optimizing your part for its necessary strength. So this over here, as an example, a um, is a steering knuckle on a go-kart. So the designer for this split it into two pieces. One of them is this forward section right here, and the other is this member that's mounted to the frame of the go-kart. The reason why he did this is because you need a lot of flexural strength on this plane for this part to be able to support the steering mechanism itself. Whereas on here you need more strength running along here to maintain stiffness in that part. So he split it into two parts. That was able to save a lot of print time and get the strength where he needed it to be. In terms of sort of creating these types of parts and joining them together, that's something that we've also, as I discussed before, that we have a lot of resources for that on our blog, and we'll continue to produce that. But when you're thinking about part geometries in 3D printing, really thinking about how your part's going to be loaded before hitting print can save you a lot of hassle, just because there are always ways to make the design more efficient and more effective. So the next big thing is warping prevention. So one thing you may be familiar with if you used FFF 3D printing before is that parts tend to warp. As you can see, this part is warping right here. And so we have a couple tips that we'd like to share about how to prevent your parts from warping. So first, let's look into why parts warp in the first place. What happens is, because parts get laid down sort of in strands of filament. So this is the black over here, you can imagine, is a strand of filament that's laid down the outside path of a part. So FFF 3D printing is based around thermoplastics. Thermoplastics often shrink when they cool, and when they're passing through the nozzle, they heat up. So once they're laid down, they want to shrink a little bit. So this strand will have sort of a shrinking force in this direction, and this strand will have a shrinking force in this direction. And now, because you're at a corner, you get a force on this side and a force on this side. Those forces essentially sum to a larger net force that sort of comes in at a 45-degree angle. And because of that corner, that's why parts start to warp. This problem ends up increasing if the cross section of your part increases over the course of the print. So if the next layer was larger than this layer, and the path was out here, then that would increase that shrinking force, and they would start to stack up. So we have 4 suggestions for how to prevent warping. The first is on the design side. So if you fillet or chamfer your parts, that rounds those corners out and ends up reducing the stress concentration significantly. So this test part that I used to test warping, just by rounding off those edges, it ends up warping much, much less than it originally did, as you can see over here. The second is sort of intuitive for a part like this, but for larger, more complex parts, may not always be the first thing you think of, which is just to print with the largest face down. This means that there's not as much of a buildup around the corners, just because the layers that are being stacked are smaller than the ones they're being stacked upon. So printing the part upside down also significantly decreased the warping. What a brim or a raft often decreases warping as well, because it essentially pushes that warping effect from the part itself to the edge of the raft. So you're sort of pushing away the problem to parts that you don't care about, and you can add a brim by selecting Use Brim in Eiger, and that is another method for conquering warping. In special circumstances where the brim may not be enough, um, or the brim may not have the geometry that you need to prevent the warping, you can make your own brim. So instead of adding a brim all around the part, I know that the warping just occurs at the ends here. So if I make larger cross-sectional faces that adhere to the build plate on either side of this part, uh, then then you can also reduce warping. So just by adding sort of these like Mickey Mouse ears to either side of the part, you can make your own brim and prevent warping. The fifth method is unique to our process, which is through fiber reinforcement. So essentially, because we're laying materials like carbon fiber, fiberglass, Kevlar into our parts, they are forcing the materials to remain stiff and remain flat. And so if I'm really struggling with a part that I may just want to print out in plastic, then I'll reinforce it with fiber to prevent it from warping. So here you can see that original design file with a carbon fiber sandwich panel on the top and bottom, and it ends up that the part is completely flat because the carbon fiber is forcing it to be that way. This lower section is just in our onyx material. So onyx in general is very, very dimensionally stable. Onyx is a chopped carbon fiber nylon mixture. And essentially that microcarbon reinforcement, even though it's not continuous, means that the parts themselves are much more dimensionally stable and stay consistent instead of shrinking as much as other plastics like PLA, ABS, or things like that do. So I've had nearly no problems of warping with onyx just because it's a very dimensionally stable material. So the next thing that we're going to talk about is tolerancing and unit tests. This is perhaps the most important lesson that I've sort of learned when working with 3D printing, because tolerancing in general for different types of machines is tricky. All manufacturing methods, and even down to specific individual machines, whether it's my, if I have a CNC machine and there's someone at a different company has the same CNC machine, just because of even just the wear and tear on the machine, or what kinds of materials they're making on it. All manufacturing methods have their own tolerance specifications. So 3D printing tolerances usually arise from gantry robustness, motor precision, and dimensional stability of the materials. So you may have noticed that on our printers we have a very robust, sturdy aluminum frame. With Onyx, our material, our primary material, we have it's very dimensionally stable, as I just discussed, and we have high-quality stepper motors that control our gantry. So that means that we can usually achieve about 50 micron precision in a part. So in tolerancing, especially if you're printing parts that are going to interface with other components, whether they're printed or not printed, tolerancing is really important, because you don't want to have to print a 16-hour print and then realize that it's wrong. So that's why we heavily suggest using what we call unit tests, where you're testing the specific fit of an interface without having to print the entire part. So this part over here was designed by Daniel. It's the sort of lens hood for a camera. One of the very important features was making sure that that hood actually snapped onto the camera lens that he was using, and that fit was correct. So the part itself takes about 4.5 hours, but he was able to test just the ring of that part, which was a 15-minute print, to ensure that the 4.5-hour one succeeded. So unit tests end up being really important exactly for this reason, because especially in manufacturing, where expediency is key and hitting the right tolerances is key, you want to be able to make sure that the way that you've designed your part will work in context. So you can ensure that large prints will come out the way you want them. When I first started 3D printing, I'd design a part, I'd print it out, I'd get really excited, put it on whatever machine I was making, and then realize that all of the holes were a little bit too small, or a sliding fit that I wanted to work didn't quite work. So by printing out very small sections of each part of the model, I was able to test the dimensions on each of those to ensure that they would work before I went out printing, a 16-hour print. So there are two sort of different types of unit tests. One of them is just confirming that sort of the section of your part indeed fits. The other one is more sort of a sequence style where you are testing multiple different dimensions to confirm which one will work best for what you need it for. So this part section is off of a jaw for a robotic gripper that's meant to grip pipe fittings and couplings. And so this unit test over here ensures that the gripper itself fits around the coupling in the way that you want it to fit. So I'll have a picture of this on the next slide. The sequence over here is a slightly different example of a unit test where I have 5 slightly different sort of sliding fit joints, each with its own tolerance. So I have this sort of female negative piece that slides onto these male connectors, and I want to make sure that I get the right sort of sliding fit. So here there's 0 clearance between the negative and the positive. Here there's 0.05 millimeter clearance, so a little bit looser, and I get progressively larger tolerance as I go down the line. So you can see me testing it right here. So I start out with the 0.2 millimeter tolerance, which ends up being very, very sort of very slidable, and then I get all the way to the 0, which ends up being a really tight fit. So that allows me to test such that when I print a geometry like this as part of a larger contextual assembly, I know exactly what tolerance I need to hit and what dimensions I need to use to get this sliding fit. So it turned out that the 0.05 millimeter tolerance gave me a sort of a tight, close fit for the slide, which is what I was looking for. So in terms of designing a unit test, it's all about identifying what sections of your part you actually need to test. So here we have this gripper for this pipe coupling. The gripper needs to grip the part in a specific orientation. So it has this feature on here that essentially wraps around this hexagonal part. So in your CAD program, just by spending 10-15 minutes either isolating that specific section of the part or remodeling the section in question to produce a very small little part that you can test can really do a lot. So again, as I said, there's either sort of a sequence or just isolating that component. So you can either create this component, test it out with different offsets and different geometries on the faces, or you can just print one to make sure it works and tinker with the geometry until you get the fit that you want. So print the test piece in the orientation that the final model will be printed in, and then you can test it on your final model. So here's just the small unit test. This took about 15 minutes to print. It fits on the coupling that I need it to fit on, and so now I can go ahead and print the rest of my jaws, and I know for sure that they're going to fit the way that I need to. So unit tests can be really, really valuable because of this, especially when you're working with fiber reinforced parts that can end up being a little bit more expensive. The parts themselves could take a day to print, and you can print out this 15-minute part that ensures that that day-long print is going to succeed, and it only takes about 15 more minutes of design time. So instead of printing a day-long part, realizing that the part itself is not going to work out, and then having to reprint that entire part, that's 2 days of printing, whereas you could save half of that by just printing a small test to begin with. So in general, the main takeaways, 3D printing, especially with Markforged printers, where we can print things like tooling and fixtures, we can print strong parts. It enables large time and cost savings because you can print parts overnight that may take a few days, few weeks to machine. And designing for that process enables sort of strong, precise, and production quality parts. So when you're designing parts with our process, consider the limitations of the manufacturing process, whether you're machining, whether you're laser cutting, whatever, and what process would be best for your design. In some cases, you may realize that a lot of the features of your part are very planar, and it may actually be easier, at least on a prototyping side, to laser cut that part. Whereas, you may have some complex geometries that would be very, very prohibitively expensive to machine that you could 3D print with our printer and have them be just as strong and, an order of magnitude less expensive than if you were to machine them. Always remember to design with a build orientation in mind. So consider, as you're starting your design for the part that you want to print, where it's going to be printing from, and use that to guide where there are overhangs, where support material may be used step by step through your design process. And then use unit tests to reduce material waste, manufacturing time, and cost. So that's sort of the end of the presentation, and now we're going to take some of the questions. We're sort of running short on time because we have to wrap it up by noon, but we'll take all the questions that we think would be valuable. Let's see. In general, the webinar will be available. We'll send it out after we upload the recording, which should come out later today or tomorrow. In terms of, let's see. There's a question with regard to print time. So, for example, a part like this was about I believe it was a 5-hour print. If you were to reinforce this with fiber, it depends on how you're reinforcing it. You could just do a sort of sandwich panel reinforcement, or you could reinforce the entire thing. If you're just reinforcing where you need to, which in this case would probably be a sandwich panel with concentric fill, then that could take, maybe 7 or 8 hours. If you're reinforcing the entire thing because you want it to be really, really solid, really robust, that could take like 12 or 13 hours. And so we sort of advise being smart with your reinforcement techniques, which we had a webinar on last month, and that will be, if you're interested in seeing that webinar, you can ask for that as well. For some of the smaller parts, so let's see. So this part, I believe in total, this took like 12 hours to print with that fiberglass reinforcement. Let's see. What is the general speed of 3D printing with respect to machining on a milling machine? So in general, this is sort of a tricky question to answer because 3D printing is a hands-off process. You press a button, you hit print, you let it be, and then you come back the next morning or later in the day and your part is printed. Machining is very hands-on, where you have to either manually machine that part or watch over the CNC machine while it's machining, and that ends up being much more labor-intensive. So time-wise with 3D printing, what matters is the sort of the cross-sectional area of the part, whereas CNC machining is more about the number of operations that are needed. So a very complex part like this would be prohibitively expensive to machine, especially if you want it out of a stronger material, because there's a lot of different operations involved, and you need to use a 5-axis CNC machine to get some of these contours. 3D printing it only takes 12 hours. If you don't have access to a heavy-duty CNC machine, then you would have to use a service. So, for example, the jaws that I mentioned, these jaws over here, this customer, Dixon Valve, was using a machining service provider before they got our printer. The jaws would take about 2 or 3 weeks to machine and cost about $900 a piece. With our printer, they're able to print a single jaw in 6 hours for about $10. So the time and the cost that they're saving is very, very substantial, because they didn't have the machining resources in-house that they could spare for machining new sets of jaws. Let's see. Why exactly did the leg guard reduce the build time from 16 days to 2 days? So this is going back to orientation. So the reason why this takes so long is that it has this big hollow cavity on the inside that fills up with support material, and even though the part itself does not change, the geometries aren't changing, it's the support material that's causing that big increase. So essentially you're filling the entire section underneath this contour with support material, such that when you flip it over, the only thing that's being supported is sort of the base features over here. And once the leg guard achieves more, achieves a higher angle, supports aren't needed. So the supports are both a lot shorter, and there's a lot fewer supports in general, and that's why the print time is reduced so much. There are some questions about adhering parts, which I did mention. There are a few different ways to sort of, if you want to print parts that are larger than the build plate or have multiple different sort of aspects to them. We have a few different methods. The first one is using Loctite. So our materials work. Loctite 401 is a very stiff Loctite that is really useful for both our nylon and our onyx that we use to bond parts together. So in a case like this, I may add some small joining features or locating features such that when the two halves of the sphere line up, I know that they're exactly where they need to be, and I can Loctite those two faces as a result. We've also just designing in bolt holes, embedding components like heat set components in is also a good way to do that. There was a question about, let's see, the designing removable supports. So basically what our supports do now is they have this sort of accordion structure. In our Eiger software, what you can do is you control at what angle that those sort of parallel accordion structures are with respect to sort of the x-axis. So for example, right now on this part, it's all parallel to this sort of whole face. If I wanted it to be perpendicular, I could set that support angle to be 90, and that may make it, that changes the removal process. So here it's really easy because it's like an accordion. You can change the way the supports are oriented if you think they'll be easier to remove with that sort of process. You can, there are a couple questions on sample parts, so you can order a free sample part on our website. And there's also a lot of information and documentation on there about our machines. Let's see. We have what is the temperature range for a part built with onyx? So This is available, all of our sort of specifications on our materials, both our plastics, nylon and onyx, and our fibers. So that's carbon fiber, Kevlar, fiberglass, and high strength, high temperature glass. Those are all available on our material data sheet online. The heat deflection temperature is 145 degrees Celsius. And we have a specialty high strength, high temperature fiberglass that boosts the heat deflection temperature to, I think, around 150 or 160. And so that all of the specifications of our machines are available on our data sheet. All right, looks like we have to wrap this up because it's going to be around noon. So we're going to have to end the webinar. Thank you for all your questions. We hope you were we were able to answer all of them, but we know we didn't get to all of them. So if you have any more questions, please feel free to contact us. Our contact information is on our website, and we'll also be sending out a link to the recording after the webinar. If you want to watch it again and you missed some things, or you wanted to write down some of the details, you can access the webinar later on. So thank you so much, and have a great day.